All right, cool. So thank you, Joe, for that introduction. So uh, I was I was anyways going to start with the context as to why I got involved and started learning about Jepsen, right? So at our previous startup, MongoDB was the main source of the main business database that we had been using for the past 10 years, I think, right? And all of our business data used to flow into Mongo. And so the scale was somewhere around, I think, 3,000. So it was a SaaS service. So somewhere around 3,000 databases because each tenant got a different Mongo database and somewhere around 3 terabytes of data, right? A lot of accumulated data over the last 10 years. It was a ticketing system that we ran on top of Mongo. So we at the time I got involved, we were running a version of Mongo which was 3.6, I believe, and we didn't use multi-object transactions because those came with a later version of Mongo. But we looked at our business cases, we looked at the errors that we were having in our uh, data processing, and we figured that we actually honestly definitely needed transactional behavior, right? Transactions over multiple objects because we had dependencies. You can imagine a case where you create an issue object and that issue object has multiple message objects. Now, if the closure thread fails when it's creating the message object, but it has already created the issue object, you kind of end up in limbo scenarios, right? So we definitely knew we wanted to move to multi-object transactions, and that is why we wanted to evaluate the upgrade to Mongo 4.0, right? And in the in the process of doing that evaluation, we actually looked at, like as Joe mentioned, Jepsen has had multiple runs at testing MongoDB, right? So we looked at the latest claims and we kind of figured that we really need to understand Jepsen to really understand what he's talking about in those blog posts, right? So that is where all of this started for me, at least, right? So, okay. So let's kind of look at what the agenda is of today's talk. So first we'll start with a quick look of what consistency actually means in a distributed system, right? What are consistency guarantees that people talk about and why it is important, right? All of us have an intuitive sense of why consistency is important because we have an intuitive sense of correctness in our heads. But what does it look like to formalize and verify that through an automated test system, right? Then we'll look at the brief, like we'll look at a brief overview of the Jepsen test suite. What are the different components that go into a Jepsen test suite? We'll look at the overall architecture, how it actually runs when you run it on Docker or AWS or wherever you want to run it. How does it look like? And what is like what is the structure of a Jepsen test? What are the things that go into a Jepsen test? And finally, we'll look at how all of this ties in with actually checking for consistency, right? So we execute a series of operations, we get results. Now, how do we verify whether those results are X consistency model, they are serializable, they're linearizable, right? How do we check all of that? So for that, there are multiple checkers that Jepsen has. So we'll look at one of them, which is interesting because it is a transactional consistency checker, right? Okay, so when we want to talk about consistency of distributed systems, right? Let's try and understand a couple of things about what we mean by a distributed system. How do we define it so that we can build upon top of that, right, as we go along. So essentially, you look at a distributed system, it is state, and that state is operated upon by multiple processes. Now, the definition of processes here is a loose definition, which is a logical single thread of execution, right? It is not tied to a Unix process or whatever, or a thread, Java thread, whatever. It is not tied to that. It's just a logical single thread of execution where every operation has to complete before the next operation can begin, right? An operation is then just a transition of state from one state to another, right? So if you consider the variable x to be a state, an operation would be write 3 into x, right? Or write the value of 1 to x, right? So that is an operation, and it transforms the state of that variable x from whatever undefined or nil or whatever it was to 1, right? Now, if we consider a key value store, right? Your operation could be set key a to value 3. Right? That could be an operation which again transform the state of your distributed system, right? Or if it's a transactional, if you want to model a transactional distributed system, then you say reading the value of a and finding it to be 2, and then writing the value of b to 3, right? Both of these operations are a kind of complex operation, right? So all of these are operations. Now, all of these operations will generate results, because that is what will happen. Your distributed, you give operations to the system will return back the new state, right? Concurrent operations is the case where, so now for example, a single register system, let's say you write the value of 3, you expect the next read to give you the value of 3, right? Because it's a single threaded, single register system. But if you have multiple concurrent threads running, right, you write a value of 3, you read it after 5 seconds, you may not get the value of 3, right? Maybe some other thread came in and changed the value of 3 to 5, right? So concurrent operations are they're defined as operations which overlap with each other, right? There is a window of time in which both of the operations could be happening at the same time, right? All right. So then a final definition is, what is a history, right? So in this context, we define the history as a collection of operations and the results, right? So if you look at an operation like this, for example, if you say increment value A3, you get something back from the system, you append it to the already existing set of history, and you get a history of operations, right? Now, all right, so this is kind of the starting point that we want to discuss about when we talk about consistency. Now let's imagine a single variable, right? A single variable, as I said, has a consistency model of you read the last write that happened, right? And if it's a single thread, single variable, single thread, you say you read your own writes all the time, right? Now, if you take consistency into account, your model changes, because now you can't guarantee that you're going to read the same write that you made, right? Now, on top of that, another layer of complication that comes in when you talk about distributed systems is the notion of network delays, right? As we know, light has a finite speed of travel. So if you invoke a write from California, and if your database happens to be in the Pacific region, right, it's not an instantaneous write. There is a delay going from one place to another, that information going from one place to another, right? So then we have to have a notion of the invocation of an operation and the completion of an operation. And they are not going to be instantaneous, right? There are going to be delays, right? And some operations might have larger delays than other operations, right? So this kind of complicates your assumptions about consistency in a distributed system, right? So now when you define consistency models, what you say is consistency model is a set of histories that follow a certain rule, right? And if like given some rules which relate operations to their results or their end state, the history of operation that you get from the system, like you execute a bunch of operations, you get state back. That history, if it follows the same rules that a consistency model defines, you say that that history was consistent, right? And if you find violations in that history, like if you find that you wrote the value of 5, but now you're getting the value of 7, right? In the same transaction, for example, then you know it is a violation of snapshot isolation, for example, right? So if you have worked with closures, software transactional memory, you know that once you read a value in a transaction, it remains the same, even if some other thread or some other transaction goes in and commits a new value, right? But if you don't see that, right, you execute a bunch of operations and you see that I got different values in the same transaction, you know it's a violation of that consistency model, or it's a violation of snapshot isolation, right? So now what are these consistency models? Like, let's look at a couple of them that are important to us, right? So linearizability. Okay, got that wrong. So if we can assume, right, that all operations take place between the time that an operation was invoked and the time that an operation was completed, right? If we can assume that, and that operation has to take place atomically, right? You can't have, like if it's a compare and set or something like that, operation has to be an atomic operation. It takes place somewhere between the invocation and the completion. So the important point here is once an operation is said to be completed, right? Once a transaction is said to be committed, every other operation, every other process should be seeing the latest value, right? So all future operations have to observe the value that was written just now, right? That is linearizability, right? And linearizability is said to be a single register consistency model, right? It generally applies to a single register, a single variable. We extend it to apply to a database by saying that the whole database is a single register, but formally it is to do with a single register's value, right? Now this is a particularly strict form of consistency, right? Because guaranteeing this consistency is hard. You have to put in checks, you have to put in a lot of orchestration to make sure that this consistency holds. Okay, so then there are slightly weaker forms of consistency also, right? For example, sequential consistency. Now sequential consistency is essentially if we say that, okay, the operations don't have to take place between invocation and completion. You could just say the operation completed and then execute it sometime later, right? We generally, like if you think about a queuing system, it's generally in sequential consistency, because even though the client has completed the operation, the effect may not take place right away. The effect may take place somewhere later, right? Eventual consistency or stuff like that, that is a form of sequential consistency, right? But here there is an important limitation or restriction which says that operations from the same process have to take place in the same order, in the process which is known as the process order, right? So if I send out 5 operations from a single process, those 5 have to be ordered. They might be ordered differently with other processes operations, right? So this is sequential consistency. Now, let's look at some multi-object consistency models. Now, serializable consistency model is one of the stricter forms of multi-object consistency models, right? And its definition is quite like deceptively simple. It just says that the only restriction on execution is that at the end there has to be some single total atomic order in which the operations could have happened, right? And if you the important point here being total and atomic, total meaning all operations need to have a total order. If you take any two operations, you should be able to tell which one happened first, right? And there should be no cycles. So like, for example, a string of integers has total order because you can always sort two numbers and there is no cycle, right? 3 is greater than 5, but 4 is less than 3 or something like that, right? That doesn't happen. So that's a total order. And atomic is essentially what atomic means, which is it either happens or it doesn't happen. Parts of it can't happen, right? You can't have 3 operations in a transaction happen, but the 4th didn't happen, for example. Right? That is not allowed under serializable. And then finally, we have snapshot isolation. So snapshot isolation is, as I said, it is what Clojure's software transactional memory aims to achieve, right? Which is whenever a transaction starts, each transaction appears to operate on an independent snapshot of the data, right? And its changes are only visible once the transaction commits, right? And if something else has changed, any variable or any register that this transaction is also changing, this transaction has to retry, right? We all know this from Clojure's software transactional memory, refs, alters, right? So that is snapshot isolation. Cool. How are we doing questions? Like, do we want to discuss questions right away, or do we want to go into, like, do we want to carry on?
Yeah, carry on, I think, Rhishikesh.
Okay, cool. Please don't hesitate to pause me if I seem to ramble on, and if something doesn't make sense for you, please try and pause me and like ask questions. All right. So then, where does Jepsen come into all of this? So Jepsen is essentially a collection of tools that some very intelligent people have come up with, and it is a set of tools for testing consistency guarantees that distributed systems can give you, right? And it does all this by orchestrating various aspects of a distributed systems which are not very easy to orchestrate, right? So for example, it can orchestrate the network to say, I want to delay or I want to emulate a slow network between distributed systems, right? So imagine a Mongo cluster. The Jepsen test suite can actually go in and manipulate the network to say, okay, maybe one of the nodes in the cluster is very slow to respond to heartbeats and stuff like that, right? If like instead of Mongo, if you can imagine something like a Zookeeper, it might actually cause real world changes to happen, which is like leader elections can happen if you don't get heartbeat signals from a node in time, right? So it can do stuff like that. It can also do more complicated fault injection, which is it can induce network partitions, right? So 3 nodes are separated from 2 other nodes in a 5-node cluster, right? So all of these manipulations it can do. And then it has tools for, so it has a language in which operations are executed. It has a language for recording those observations, and then it has a tool for actually formally verifying whether these consistency models are violated or not, right? So it will take a set of operations, it will generate a graph, and then it will look for cycles in those graphs, which actually say, okay, because we saw this read write cycle, or we saw this write write cycle, this is probably not, this is not even repeatable, or this is exhibiting dirty writes, for example, right? So all of that formal verification also the Jepsen test suite can do, right? So the Jepsen suite itself is just a closure library, and you use it to write tests for the subsystem that you want, right? L is the verifier. It is known as checker in terms of Jepsen language. So L is the transactional consistency checker. So it can check for consistency violations in multi-object transaction operations, right? Maelstrom is interesting. It's kind of like a test bed where you can develop different distributed systems, toy implementations, and you can actually run Maelstrom very quickly to see whether your toy implementation is violating certain consistency guarantees, right? So, for example, I think Ernesto is on the call. So we were part of a group that we were running through the distributed systems course that MIT has, right? So one of the assignments in that was to write a raft implementation in Clojure, right? Like we were doing in Clojure, the students generally do it in Go or something. So if you have a toy implementation like that, right? Imagine being able to put it into a system like Maelstrom and being able to run tests to see whether your raft implementation is actually correct or not, right? Then there is Nosos, which is an earlier version of consistency checking, but it checks for linearizability. So it's kind of a single register system. And then there are test suites. So if you look at the repo in Jepsen IO on GitHub, there are test suites for each individual system, right? So there are MongoDB tests, there are raft tests, there are Zookeeper tests, right? So that is another important component in the Jepsen suite. All right, so then let's look at the architecture of a Jepsen test when it actually runs, right? So a Jepsen test runs as a closure process on a control node, right? And the control node uses network implementations to actually log into database nodes, and those database and log in and also configure the database nodes, right? Now, once the system is up and running, the control node spins up single-threaded logical processes that we talked about earlier, right? So it spins them up. I think one for every database node that we have, one client for every database node, right? And then there is something known as a generator, which generates operations for the client to execute, right? So it generates a stream of operations. An operation is randomly given to a client, and the client interacts with the database, runs those operations, and returns back whatever completions the database return, right? So simply put, a client is essentially going to be the one talking to MongoDB and doing inserts and stuff like that, and just based on what it got from the database, it returns it back as a completion, right? And all of that gets recorded as a history of operations, the history that we talked about earlier, right? Then there is something interesting known as a nemesis, right? Now, nemesis has two parts. One, nemesis is also, there are nemesis generators, which generate which generate fault operations essentially, right? So a nemesis operation might be kill, right? Which kill essentially means kill the database process on any random node, right? So that's the nemesis operation, right? So imagine interleaving normal operations with nemesis operations, and then there is a nemesis client, which actually what it does is similar to what a normal client does, but uh, instead of executing operations, it actually executes nemesis commands. So it is the one that actually goes in and deletes the database process, or if it's a partition, then that client actually goes and manipulates the network to create partitions out of these database clusters, right? So that's kind of how a Jepsen test looks like at runtime, right? So I guess that's pretty much what I wanted to talk about the architecture. Okay. Any questions so far? Should I look at the chat? Anything there? No. Okay. Any questions so far?
Yeah, I was just wondering. Can you hear me?
Yeah, go on.
Like you can probably sort of simulate this in real network, sort of bring up machines in AWS or something, or you can probably simulate this on your own machine. So how does it do it? Sort of does it use Kubernetes on my own machine, or like how does it do sort of the separation?
Sure. So the short answer is it uses IP tables, and yes, it can do it both on your local. The example uses Docker Compose networks, but I'm sure there must be ways to do it in a Kubernetes cluster also. But essentially, if you look at the NOAC test, if you look at the network implementation, this is IP tables. So these are the actual commands that it executes. So IP table, drop, or it can do TC. So these are the commands that it actually executes from the control node to manipulate the network. So like you can imagine a different implementation of the same protocol, and which is this protocol, right? So you just have to implement this protocol, and then you can have a Kubernetes network manipulator, for example.
Okay, thanks.
Cool. So, all right. So then, what does a Jepsen test actually look like? So Jepsen test essentially is just a map with all of these keys, right? So this is the default test map that we just looked at. So there are multiple components to this Jepsen test which we can look at. The first one is a database, right? So the database is just a protocol which has to be implemented essentially for setting up and tearing down the database. So this is the MongoDB test, for example, right? Now, if you look at so if you look at DB, right? So this is a Mongo database. Where is it? Yeah. So this is the Mongo database implementation, right? So it has functions for setup. It has functions for teardown, right? Essentially, just in setup, you are supposed to run all the operations that are required for setting up your database. So here you can see stuff like configuring Mongos and starting Mongos, and then you add the shards essentially to create a Mongo sharded cluster. And teardown is just you stop Mongos and you remove all the log files and stuff like that, right? So this is an example of the database protocol, right? So next is a client, right? Now the client is, as we discussed, client is just a protocol which implements operations which are actually run against the database, right? So what are the operations that are required to access the database by Jepsen? Those are what a client implements, right? And what the client actually does is it takes all the operations, the series of operations that we talked about that come from generators, and it applies them to the database, and then it returns back the results from those operations, right? So if we look at the Mongo client, right? Yeah. So if you look at the Mongo client, for example, right? So here you can see this is open. Anyways, but like this namespace essentially implements interaction with Mongo, right? And the protocol essentially has a bunch of functions that we can probably see. Hold on. Now I can't find it. This is the client. Sorry. Yeah, so this is the Mongo client, right? So it has an open which creates the Mongo connection. It has a setup which creates the collection that this test wants. It has the invoke which actually runs the operations that you generate in a transaction, right? So here you can see it is actually executing transactions. This is a Mongo API for executing transactions, right? So this is the client implementation. Then there is an OS implementation. OS is essentially for setting up functionality for operating system setup and teardown, right? So the default OS that most tests use is Debian. So you can look at the Debian OS here. So this is the implementation. So for example, you set up the Debian node, you set up the node with Debian and you install these packages. So these are the packages that are required for all database nodes and control nodes. Actually, only database nodes. The control nodes are set up differently, right? So this is the OS package. Then there is, as we looked at, there is a net package for manipulating networks. There is the generator for generating operations, right? Essentially, a generator's job is to specify what invocations to perform, and also there is another complication of when, right? You might want to have delays between two operations before executing the next one, right? So essentially, the operations that the generator generates become the history that you check for consistency, right? So there are multiple default generators that Jepsen comes with. You can just take a simple map is also a generator because the only value it generates is itself, right? Or you can have sequences which are essentially sequences of generators. So you take operations from one generator, then you move on to the next one, right? Then there is the Nemesis, which, as we discussed, it's a special kind of client which only executes Nemesis operations. So it will only execute network partitions. It will only execute the process kill operations. It will execute operations like slowing down the network and stuff like that, right? And finally, there is the checker, which is, it essentially takes the history of operations and it can check for various consistency violations, right? So let's probably, if we can look at an example. So something like this can also be a generator, right? So this is essentially you create a map of create a sequence of operations of this form, write some random value between 1 and 5, 0 and 5, whatever, right? And then what you can do is you can do something like this. No such namespace, of course. What is it taken in as gen? Is it gen? Yeah, okay. Yeah, right. So as you can see, this is what Jepsen uses to generate the operation. This is something internal to its own implementation, which is the state of the generator for the next operation that it wants to generate, right? So you keep generating values like this, right? All right. So yeah, so then this is essentially a high-level overview of what a Jepsen test looks like, right? So then Jepsen has internal functions to take this map of the test and pull operations from the generator that you have defined, provide them to the client, execute those operations, record the history, and then call the checker when all of the operations are done to verify whether consistency was violated or not, right? And of course, in between all of that, insert nemesis operations to manipulate the network or bring down the database, bring down the entire cluster, stuff like that, right? Yeah, I think this is about it from a Jepsen test point of view. Do we want to take questions now, or there is another small part which I could discuss if we want to?
So given it's about 45 minutes in, maybe we can take a couple of questions and see if is the next part. Did you want to show a demo as well, or there's no?
There is a demo that I can show, but like give me 2 minutes to set it up. It's on my Linux laptop due to some.
Well, in the meanwhile, if people wants to ask a question.
Yeah, please go on.
I have one myself. It's nobody else.
Yeah, go on.
I have a question.
Go ahead.
Oh, sorry. I was going to say, so you were looking into the consistency properties of MongoDB in the project you spoke about. What did you find after using the Jepsen suite? What kind of conclusions did you come to, or is that actually what you were about to move on to?
Yeah, so that is essentially that was the last part of my agenda. If we had time, maybe we can do it.
Ignore the question then, please. Take Renzo's.
Yeah, we can do, like, if it's interesting enough for people, we can probably do another session.
Yeah, it depends. Yes, if you think that it's not like enough time to set it up, then of course yes. My question was, so you gave us an introduction to the theory of consistency, linearizability, serializability. So these important concepts. I'm just trying to understand how important it is for you to master those concepts in order to use Jepsen. Is that something that you have to understand?
You have to understand at a high level. So you have to understand it because essentially the aim of running the Jepsen test will be to somehow figure out figure out what level of guarantees the database or the distributed system is giving you, right? For example, when you talk about, for example, Mongo, right? The findings that Jepsen had from running the Mongo test said that there is a cyclic information flow, right? Cyclic information flow essentially is a technical term to say snapshot isolation is not guaranteed by MongoDB if you even under network partition conditions, even if you use the highest read and write concerns, right? So you have to understand what snapshot isolation means, because that is where your business logic will be affected, right? When you're writing, when you're writing a closure transaction, for example, if you don't know what guarantees you're getting in the transaction model, you'll probably write the wrong code. So I would say you have to understand it from a practical point of view. You don't have to understand. You don't have to understand the paper on which all of this is based. For example, so L is based on a paper which uh, defines consistency in terms of a connected graph, right? So those are very complicated things which we probably don't need to understand, but we need to understand at a practical level what it means for the system to not be snapshot isolated, right? It essentially means that you might read the value of a key to be 5 at the start of your transaction, but at the end of the transaction you might read it to be 7, right? Because it is not snapshot isolated. Somebody else came in and committed a value of 7 to the register that you were reading, right? So those are the kinds of details that you have to understand, probably, is what I would say. But to run the Jepsen test, you essentially just need to understand the Jepsen language, right? So what does an operation mean? What does a completion mean? Stuff like that. Hold on,
Yeah, sort of more of a general question. So my understanding so far is that sort of for these 7 things you represented now, like Jepsen sort of has like a protocol that then you can implement for your specific use case. And you can also say, hey, I'm not interested in implementing it. And then you just say it's like a no-op and it uses some default thing. Is that sort of about it?
Yes, so there are defaults for certain scenarios. Like as you saw, there is a default for the Debian OS, or there is a default for the IP tables network implementation, right? But there are you still have to have a generator, because you have to define what operations you want to test in your distributed system. So when you define the operations, you also have to define the client, because the client is the one who understands those operations. The client is the one who will execute those operations against your distributed system. So I would say at a minimum, you need a generator and you need a client to run. And of course, you need a database system, right? So those 3 things probably are the minimum that you need for implementing or running a Jepsen test.
And it's sort of, is there always only just one client? That seems sort of like a bottleneck. I mean, often systems have also multiple clients, or?
No, so there are multiple clients that the Jepsen test suite creates. I think, if I'm not mistaken, there is one client for every database node. So
I see.
That's how it works. But yeah, there are multiple clients that can run at the same time. Do we have time to look at a demo, or do we want to stop today?
No, I think another 10 minutes are good.
Okay, just give me 1 minute to set up Zoom screen sharing.
Is there time for another question in that minute?
Yeah,
Or is
go
that
on.
pushing it? I was going to say, I guess Jepsen is. I actually don't know when it was first released, but I guess it's probably been out for a number of years now. Are there any other tools that have sprung up since that you're aware of that sort of operate in a similar space? They're designed for testing properties of distributed systems, or any other adjacent tools?
Good question. I don't like. I haven't run across any others yet. Maybe like I don't know. Maybe Netflix is what was that Chaos Monkey? Maybe that comes close, but I don't know whether it aims to do the same level of formal verification that Jepsen is doing for distributed systems.
That was definitely the impression I got about Chaos Monkey, was that it sort of seemed like it was testing your operational response to failure as opposed to specific isolatable properties. Still useful, but I guess it's definitely not quite as strict as something like Jepsen.
Right.
Cool.
Right. Cool. Let me attempt. You cannot start screen sharing. Of course, because I'm sharing my screen. Okay, so I've stopped screen sharing. Let me attempt to start screen sharing from here. How do you? All right, let me share this. Okay. I assume the font is not legible.
I think it's okay. I don't know if.
Looks okay to me.
Okay. All right. So then this is a toy example of a Jepsen test suite that I wrote for closures software transactional memory, right? So if you look at the test, it essentially is just a single database node. Okay, let me go to a different, because this is connected to the REPL. Yeah, so this is a fake database. Essentially, it does nothing because there is nothing to do. Everything is local. Then there is the client, which is it's a list append client, right? So I didn't have time to go into list append workloads and why they're needed, but let me see. So essentially, list append workloads are transactions of this form, this, right? So this is a transaction which appends the value 2 to a register by the key. So this is key and this is value, right? So it appends 2 to the register with key 1, and then it reads the value of 1, right? So let's see if this runs. Yeah. So this is the completion that it returned, right? It said, okay, I appended 2 to the value 1, and the read is now returning 2. Now, if I do 3, the read is now returning 2 and 3, right? So you can then have multiple, for example, you can say read the value of 0, right? So it will say 0 is actually nil, right? Then you can say, okay, another transaction that I want to do is I want to append 1 to the key 0. So now this is still returning 0 because at the time it was still 0, and now it appended 1. So this is what you get. right? So these are the kinds of transactions that they are known as list append transactions, where every key has a vector value, and the only operation you can do is append to that vector. Right? This is important from a point of view of essentially it is known as traceability and recoverability, where you say that once you read the value. So for example, once you read the value 1 from the key 0, you know that so if you can say that there is only one transaction which actually writes the value 1, then you know which transaction came before this one, because I read a value that somebody else wrote, right? Now if I read the value 2 and 3, I know that there was a transaction which appended 2, and then there was another transaction which appended 3, right? So this is important from point of view of building that graph which I talked about, and that graph is essentially what the L consistency checker goes through, and if it detects cycles in those graphs, it knows that there was a violation and stuff like that, right? So let's look at this simple example of a list append client which operates on a ref, right? Which operates on a closure ref. So in the invoke function, all it does is it takes transactions and it runs those transactions. It runs those transactions, as you can imagine, in a single do sync block, and part of running the transaction is essentially to the read transaction is just getting the value, the write transaction is doing a conj, right? Simple, obvious stuff. What you can do now, so this is a Docker-based setup. Jepsen comes with 3 kinds of setups. One is an AWS setup where they have their own AWS marketplace. I don't know what that is, package maybe. They have a marketplace package which you can just deploy, and it orchestrates all of this for you. The second option is Docker, where it uses Docker Compose to spin up database nodes and then spin up a control node. And then the third one is LXC, which is Linux containers. That is actually more stable than the Docker one, but I couldn't get it working on my Arch Linux setup. If I spend more time, I will probably get it working. Right. But yeah, so let's run the test now, right? So this is how you run the Jepsen test. It will tell you what OS and what stuff it is using, and then these are all the transactions that it is executing, right? So if you see, sorry, yeah. So if you see transactions like, so it invoked an append on 26 with 4, and then read 26. And what it got in return was the OK one, which is the result of the completion, which said, okay, I appended 26, and then I read 26 as 1, 2, 3, 4. Right? The next transaction it executed was read 24, append 1 to 27, and stuff like that. So all of these operations are coming from the generator that we have defined, and that generator is just a simple generator. There are no nemesis right now, and it is staggered based on a rate of operations that we can define, and it runs for 10. It runs for 10 seconds. So if we increase it to 50, for example, I'm probably, yeah, okay, I'm in the right file. So if we then it can execute for 50 seconds, right? So you might want to run a test case for longer just to see whether the system still behaves as expected, right? Or you may want to run a short test. Or so what you can do to enhance this is probably have some kind of nemesis. But for closures, for the toy implementation that I was writing, it doesn't makes sense to have nemesis, because what is the nemesis going to do, right? This is an in-memory ref which nobody else has access to anyways, right? Yeah, so this test is still ongoing. Can stop it now. Cool. I'll probably leave from this session. Yeah, okay. I'm done.
Well, thank you, Rhishikesh. So we are about the time. I would say that if there is any other question, maybe we can take it on the chat and offline. If you can maybe post that paper that you were mentioning, a link to that, that would be interesting anyway, even if it's not requested.
Sure. I'll actually post
the...
links to all the reference material that I use to study and come up with this also. I'll post all of that in Slack.
Cool. I'll stop the recording.